OK 啊，各位参赛者，大家这个晚上好啊！然后欢迎大家参加咱们这个2024的波海黑松第二场的 workshop 直播活动。然后我是主持人 Tracy 啊。对，咱们这个2024的黑客松啊，分为这个新加坡和曼谷啊。对，然后 workshop 都是在一起的。然后这次活动呢，也是我介绍这块儿还是按照中英文啊，然后一会儿咱们两位老师按照自己的这个语言来介绍啊。行，然后Polkadot Hackathon 呢是 OneBlock 举办的一个波卡生态开发者的创业大赛，然后招募面向全球的 Web3的技术爱好者参赛，然后促使这个开发者们为波卡 S 生态创造出更多的产品，然后带领团队投入到这个波卡岛的生态开发者建设当中。然后 OneBlock 呢，官方也会在这个黑客松举办周期前后啊，协助咱们开发者组建团队，提供技术指导。引入这个投资等扶持啊。这里也提醒一下各个团队啊，大家创建好自己这个 GitHub 仓库之后啊，要按照这个参赛规范啊，提交完整的一个项目信息。这是官方评为审核作品的地方。如果有任何疑问呢，在合同参赛群内啊，咨询老师或者工作人员都可以啊。然后另外呢，呃，咱们黑客松和曼谷这两个大赛加起来啊，4个赛道，奖金池总共是63万美金，而且可以和 Bounty 叠加。在这里呢，先预祝大家取得好成绩啊！Dear participant, good morning and good evening, and welcome to the second workshop live broadcast event of the 2024 Polkadot Hackathon. I'm your host Tracy. Polkadot Hackathon is an entrepreneurial competition for Polkadot ecosystem developers officially organized by OneBlock. It recruits Web3 technology enthusiasts from the world to participate, promoting developers to create more innovative products for Polkadot and substrate ecosystem, and leads the team to invest in Polkadot ecological development and construction is on our way. One block will also help developers create teams, provide technical guidance, and introduce investment and other support before and after the hackathon. Here we also run each team that after creating your GitHub repo, you need to submit complete project information following the competition specifications. There's where the official judges review your project. So if you have any questions, you can consult the mentors or the stuff in the hackathon group. In addition, the total bonus pool of these 4 major tracks of the 2 hackathons is 630,000 US dollars and can be stacked with a bounty bonus. Here, I wish all projects team good luck. 然后咱们这个黑客松举办6场啊，今天是咱们第二场，然后是波卡生态的这个贡献者啊，为大家带来这个内容分享。对，就是周六周日嘛，下周还是同一时间啊，大家也记得关注一下。对，OK, so we have a total of 6 online workshop we're holding during the hackathon. Today is the second workshop. There, yeah, so our Polkadot ecosystem contributors will share contents with you. 然后咱们这还有一个打卡规则啊，打卡规则就是，如果您想分享这个 Travel Grants 啊，您需要参加至少3场这个 workshop，并且进入决赛，而且来到线下啊，就可以瓜分这个 Travel Grants。所以大家记得这个一定要打卡。然后打卡规则呢，就是大家可以看啊，就是用您的这个姓名啊加项目名称，或者如果您现在还没有这个项目的话，您的姓名加个人就可以打卡了。It's a reminder for everyone, teams that participate in 3 online workshops and check in and then successfully enter the finals and participate in the offline demo day can share the travel grants pool and the rules listed here. If you have a project, please send your name plus your project name. Or if you don't have projects, please send the name plus individual in the comment area. 行，然后今天呢，咱们活动啊，就是有咱们2位老师啊，咱们 Acala 工程师书记老师，还有 Brian Wu，from Chris 核心开发者啊。行，然后大家可以有什么疑问啊，可以进行记录啊，然后 每位老师分享之后啊，咱们都有一个 Q&A 环节，我会给大家同步一下大家的疑问。So, yeah, we have the sharing session, and we are very honored to invite Substrate contributors to participate in this workshop and bring you rich thematic sharing. Their sharing contents covers various fields and tracks that everyone is concerned about, and I believe it can provide valuable experience and inspiration for everyone. We have Shunji, full stack engineer of Acala, and Brian Wu, Crust core developer. Bring you the theme sharing, and during the periods, if you have any questions, you can write it down or just drop it in the comment area and then forward to our speakers. 行，那咱们就进入这个第一个环节啊，由咱们这个老师顺吉老师跟咱们带来主题分享啊，资产路由器。Okay, let's start with the first part. Shunji, full stack engineer of Acala, will share with you the asset router. Okay, 您可以分享。
Oh, okay. Hi everyone. So I'm gonna share my screen right now. Yep. Can you see my screen? If you cannot, please let me know.
Okay, I can see it. Perfect.
Cool. Thanks. Okay, let's get started. Hi everyone. My name is Shunji, and I'm a full stack engineer at Acala. Today, I'm happy to share with you the multi-chain asset router on Acala. So what is a multi-chain asset router? It's basically a smart contract that is deployed on Acala EVM Plus. And this contract can automate transactions for users. So a user only need to sign one transaction to complete a bunch of actions. And even in some cases, the user doesn't need to sign anything, and the contract can perform some general purpose transactions for the user. So for example, let's say we have 100 dots on Polkadot, and we want to do liquid staking on Acala and get the liquid version of dot, which is called L dot. So usually we need to sign two transactions. First, we need to do an XCM transfer that cross-chain transfer dot from Polkadot to Acala. And after the dots has arrived at Acala, we need to sign the second transaction, which is to liquid stake dot on Acala, then get L dot. As we can see, this requires multiple signatures, which is not a super smooth user experience. And now with the asset router, the whole process becomes much simpler. We only need to sign one transaction on Polkadot, and that's all. So after a short period, we will get L dot directly on Acala. That's because the asset router completes everything needed for us under the hood, and users shouldn't even know the existence of the asset router. The one I just mentioned is the most basic asset router. It's called HOMA router. So HOMA is the protocol name for the liquid staking on Acala. And so that's why we call this HOMA router. It basically routes dot to the HOMA protocol. So besides this basic one, we have implemented many other types of asset routers. They serve different purposes. And there's one common thing about them. The user only need to sign one transaction, usually on other chains. And everything happened on Acala is handled by the asset router automatically. So user doesn't need to sign anything on Acala. Let's take a look at how these other asset routers look like. First, we have the XCM router. Let's say we hope to bridge Ethereum or any other ERC20 token from Arbitrum to any parachain. Unless the parachain itself is connected to Arbitrum, which most of the parachains do not, so there's no direct route to do that. And usually we can first bridge from Arbitrum to Acala through wormhole bridge, and then redeem the token from wormhole as the second transaction. And now the token should have arrived at Acala. We can then use XCM to cross-chain transfer to other parachains. So this whole process requires signing 3 different transactions. And what's worse is that we need to use 2 different wallets. So transaction 1 and 2 are signed by MetaMask. And the last one is a substrate transaction, which is usually signed by a Polkadot wallet. And what's more, we not only need 2 different wallets, but also need to go to 2 different UIs to complete the whole thing. First 2 transactions are on the wormhole UI, and the XCM transaction is on the Acala UI. So we can see the whole flow is very inconvenient. On the other hand, with the help of the XCM router, we only need to sign the first wormhole transaction once, and the token will eventually arrive at the target parachain automatically, which is a much better user experience. And next we have the wormhole router, which is very similar to the XCM router we just saw. And in fact, it's the reversed version of the XCM router. Let's say we want to bridge tokens from a parachain to Arbitrum. Without the asset router, we need to first transfer a token to Acala with XCM, and then bridge the token through wormhole to Arbitrum, and finally redeem the token on Arbitrum. It's again 3 different transactions to sign. And with the help of the wormhole router, only transaction 1 is needed on the original parachain, and the token should arrive on Arbitrum directly. We also have this Euphrates router. Euphrates is the farming protocol on Acala, on which user can stake their dots or L dots or some other tokens to do some yield farming. So suppose we have some dots on other parachains and hope to first liquid stake them to get L dot, and then stake the L dot on Euphrates to gain some extra yield. This involves several steps. So first we need to XCM transfer to Acala and then do the liquid staking. So if you remember the first 2 steps are exactly the same as the HOMA router. But this time we have 1 step further, that is to stake the L dots to Euphrates. So the Euphrates router is like a extended version of HOMA router, that it can automate this 1 more extra step to stake L dots to Euphrates. So as a user, we only need to sign the first transaction, and at the end of the day, we will have the L dots that are already staked on Euphrates, and they are already generating yields for us. Okay, lastly, we have the swap and stake router. This is a more advanced version of the Euphrates router that we just saw. So basically, this router does everything the Euphrates router does, but it has 1 extra feature that you can probably guess from the name. It swaps a small portion of the token for ACA, which is the native gas token on Acala. This is especially useful for new users on Acala. For example, if you are a Solana user and want to stake your Jito on Euphrates, you probably don't have the ACA as gas token on Acala. So after staking to Euphrates, you cannot even withdraw it or do any other transactions, because there's no ACA token on your account to pay for gas fees. So since we have this swap and stake router, we should be able to do the bridge and stake Jitoso from Solana with just one click, and also receive some ACA gas drop on the Acala account. So now we can do unstake or do any other operations on Acala, such as swap our Jitoso to any other tokens. Cool. So we have seen all the types of asset routers. You might be wondering how they are implemented. So next, I will introduce some technical details and how the whole flow looks like under the hood. There are essentially three components. We have the asset router contract, the relayer, which is a Node.js service, and the user interface. For the asset router contract, we have two different types of contracts. One is the factory contract, and the other is the actual router instance. The factory contract can deploy the asset router instance based on the router instructions, such as what's the recipient address. And for each set of instructions, there will be a unique router address, and a factory contract will deploy the router instance to that unique address. So in other words, each of the router instance has a fixed instruction, and different instructions will produce different router instances on different addresses. And then once we have the router address, we need to send the tokens to that router address so the router can do the routing for us. For example, for the HOMA router, we will cross-chain transfer dot to the router address first, and then the router will perform the routing with the given instructions. So in this case, it's HOMA router, and what we want is the liquid staking. So the router instance will first liquid stake dot and get L dot, then it will send the L dot to the recipient address from the instruction. Cool. So besides the contract, we also have the relayer, which is a Node.js backend service. There are mainly two reasons that we need this service. First, we want to encapsulate the interactions with asset router contracts. So the user interface doesn't need to care about any of the low-level details to interact with the contract. It can just call relayers endpoints to complete the whole routing process. And the second utility of the relayer is that it can pay for the transaction fees involved in the routing. So basically, after the UI posts a routing request to the relayer will call the factory contract to deploy an asset router instance and call the route method on the router instance. Yeah, so basically the relayer is the initiator of all these transactions. And that's why users don't need to do anything. The relayer automatically triggers all the necessary steps for users and pay for the gas fee. Okay, the last component is the user interface. It will first query relayer to get the router address based on the instructions, and then prompt the user to sign a transaction, which will send whatever token is needed to the router address. And now the user don't need to do anything else. Just wait a little bit. And after the token has arrived at the router address, the UI will send a post request to the relayer to trigger the routing transaction. So now we are familiar with all the components. We can take a look at what the whole stack is like under the hood. So let's take the HOMA router as example. So the user will first connect his wallet to UI as usual. And then UI will send a GET request to the relayer. And in this case, it's HOMA router. So the endpoint is called should route HOMA. And we need to add the instructions as parameters. In this case, we only have the instructions only have one parameter, which is the recipient. So after the relayer has received this request, it will interact with the factory contract to dry run deploy router method. So in this case, it's not actually deploying the router yet. It's only dry run the method, and this method will return the router address to us. So the relayer will return the router address to the UI, and now the UI know where to send the token. It will prompt the user to sign an XCM transfer transaction. So this transaction basically send the user's dot to the router address. So after the user sign transaction, the UI will wait for a little bit until dot has arrived at the router address and so ready for the routing. And now UI will do a post request to the relayer. And in this case, it's called route HOMA with similar instructions. So it will pass the recipient address. So now the relayer has received this post request. It will again interact with the factory contract and call this deploy router and route method. This method will do two things. First, it will actually deploy the router instance to the router address, and then it will trigger the route method on the router. So the router will do the routing according to the instructions. So in this case, in the HOMA router, it will stake dot and get L dot, and then it will send L dot to the recipient in the instruction. So now the whole routing process has complete. The router instance will do a self-destruct. This is to refund the storage fees, so we can save some gas. And so now relayer will return the transaction hash to the UI, and UI now knows the whole routing process has completed. So it will tell the user, hey, your L dot should already arrived at your account. So yeah, that's basically the whole flow for HOMA router. And for other routers, it's essentially the same process, but the instructions and endpoints will be slightly different. For example, for the U-Free router, we need to specify which pool to stake the token in, because there are a couple of different pools for U-Free. So the router need to know which pool to stake. And so the instructions for U-Free router will be recipient address plus the pool ID, which is slightly more complex than HOMA router. But the whole flow is exactly the same. We first compute the router address and then send token to that address and trigger the routing. Then the router instance will do whatever to do based on the instructions. Okay, so for any smart contract, one of the most important thing is safety. And the SI router has a couple of features that ensures users' funds are 100% safe. First, there is no single point of failure. So usually the relayer will trigger the route, the route transaction for the users. But that's only for convenience. So users won't need to worry about this part. But this operation is actually permissionless. So even in the case relayer is done, user can still trigger the route himself very easily. The only cost is just a couple of cents of the transaction fees. Yeah, usually relayer pays for this fee. And yeah, so it's permissionless. The routing process is permissionless, and the token will never stuck in the router. Also, each router instance is programmed to only be able to route the asset to the target account, which is basically the recipient in the instructions. As we mentioned before, each instruction and the router address is one-to-one relationship, which means for each router instance, the instructions are fixed. And since it's non-upgradable and there is no admin account for the router, no one is able to steal any token from the router. It can only execute the route and send token to the predefined recipient in the instructions. And what's more, everything is immutable, including the fees. So there is no way anyone can increase the router fee and rug all the tokens from the router. So if we ever want to modify the fees, we need to deploy a new fee registry contract. Yeah, so these features are the safety guarantee for user funds. So what we have seen so far is the current version of SI router, and it's still in a early stage. In the future, it might evolve to something more interesting and more powerful. For example, we can build a cross-chain any token to any token swap that we can, let's say, swap USDC on Base to DOT on Hydra directly with one click, one signature. Yeah, this will be super cool. And what I imagine as the ultimate shape of the SI router would be something like a multi-chain intent-based router. So imagine if we have a goal or a intention that requires several steps to complete. Usually we will first we need to find out the path ourselves. You know what to do first and what to do next. We need to figure out the whole sequence of transactions, and then we need to go to different UIs to complete each of the steps, which is a super tedious process. However, with a intent-based router that integrates all the required protocols, we can probably achieve the whole thing with one click. And similar to the routers we have seen, we just need to send the initial tokens to the router address, and the router will just complete all the steps for us, everything at once. So yeah, this would be my dream user experience. I'm looking forward to seeing something like this in the future. And here are some links if you are interested in more of the technical details. So we have this SI router GitHub and relayer GitHub. So if you are interested in the codes, how they are actually implemented, feel free to check out the GitHub. We also have some documentations in our EVM doc. So if you are interested in more detailed explanations, or if you are interested in learning more about the SI router, feel free to check out the doc. Cool, and we have the bounty price up to $3,000 worth of ACA token. So welcome to participate. Yeah, that's all for today. Thanks everyone for joining.
Okay, thank you, Xunji. For now, I haven't seen any like questions. So yeah, I guess I can just share my screen. Yeah, just remind you that if you want to get the travel bounties, you have to drop your name plus your project name, or your name plus individual. Yeah. So，大家如果想参加这个 bounty，就是 travel grants 啊，现在把您的这个姓名啊和项目名称，包括或者姓名个人啊，发在评论区。行，那咱们接下来就有请咱们下一位老师啊，Brian Wu Crust 核心开发者啊，给大家带来这个 Crust Network 详解。OK，next Brian Wu Crust core developer will introduce Crust Network。好，OK。这个退出分享。
Okay. Okay. Thanks for one block. Second, let me share my screen. Okay. Can you see my screen?
Yes.
Okay. Let's get started. My name is Brian Wu, and the core dev of the Crust Network. Today, I have a brief introduction of Crust Network, the decentralized storage solution for Web3. We'll divide today's sharing into 4 parts. First is the Crust Network introduction and overview. Second is the technology stack introduction, including the IPFS, Meaningful Proof Work, the GPOS. Part 3 is the Crust Network products brief introduction. Part 4 is how to develop and build with the Crust Network SDK and API. Okay, let's go to the first part. Crust Network is a public blockchain built with the Polkadot substrate framework. It provides a decentralized storage solution and dependent solution for Web3 ecosystem. It uses IPFS as its underlying storage protocol and exposes instant and accessible on-chain storage functions all over the world. Now the whole network has over 700 terabytes storage capabilities and over 1,500 physical server nodes across all over the world. It is permissionless to join the Crust Network to provide storage power and earn CRU tokens as rewards. The more nodes we have, the more decentralized it is and the more trusted it is. The Crust mainnet blockchain builds on top of IPFS, the storage proof module, the blockchain consensus module, and the storage market module. It provides comprehensive SDK, API, and products for both the Web2 and Web3 ecosystems. Crust Network can be used in a wide range of scenarios, including DApp hosting, NFT storage, and trusted storage, and so on. For DApp hosting, Crust can provide better security for DApps and can prevent issues like DNS hijack and downtime. For NFT, it can provide guaranteed and verifiable storage to ensure the NFT contents ownership. And for trusted storage, Crust can provide trusted and, more important, auditable trust on technologies, like the sensitive data like KYC documents and accountable data like the carbon footprints. Crust Network has integrated with the most popular Ethereum-based chains and Polkadot-based chains, like Ethereum mainnets, arbitral optimisms, and like the Moonbeam and A-Star algorithm on Polkadot World. And we also have a large amount of users from different Web3 domains. For example, in DApp hosting, Uniswap and AV has deployed their website front ends on Crust, NFT storage, NFT scan, unique art are users. Also, there are many more other users in general Web3 storage domain. Crust has built up a big ecosystem right now with over 150 projects and partners, and is continuously onboarding new partners and users. Next, chapter 2, let's have a deep dive into the technology we are using in the Crust Network. Crust Network works in 5 layers as described in this diagram. Let's see from bottom up. The IPFS, the Interplanetary File System, this is the underlying storage engine and protocol for Crust Network. We have customized the standard IPFS protocol to fit in the Crust Network requirements. The second layer is the MPOW, the Meaningful Proof of Work. Since it's permissionless for any physical servers to join as a miner to provide storage power, we need a zero trust storage proof layer to inspect and prove storage work of miners. To avoid any cheating and scamming, we use the TEE, the Trusted Execution Environment technology to do the proof of work. The middle layer is the GPOS, the Guaranteed Proof of Stake. This is a POS-derived consensus layer that requires nodes to provide storage proof to get staking quota. GPOS is the mechanism that a miner can get CIU tokens as rewards in a fair manner. The one provides larger storage volume and stores more files can get more rewards. It is built on top of Substrate baby and grandpa algorithms. The next layer is the DSM, the decentralized storage market layer. It maintains a storage order pricing and rewards mechanism and enables users to place storage orders on the chain, which can then get their data stored and distributed across the network. The top layers are the products built on Crust Network and SDK, which we will talk about in details in chapter 3 and 4. Now let's go into details about each layer in the next few slides. Let's see what is IPFS. Named Interplanetary File System is a decentralized storage and delivery network which builds on fundamental principles of peer-to-peer networking and content-based ajaxing. In traditional client-server HTTP model, it is centralized, which all server users access a single data center to get data. But for IPFS, it's a peer-to-peer model. No central servers, all servers are equal. IPFS has no single point of failure, and users do not need to trust each other, so making it more reliable than traditional systems. IPFS also eliminates the problem of DNS hijack by allowing data to be adjusted by its contents rather than by its location. This is the so-called content-based ajaxing. So in other words, content in IPFS is still reachable regardless of its location and does not depend on specific servers being available. Generally speaking, a basic IPFS workflow includes 4 parts between the content producer and consumer. First, the content owner upload the contents to IPFS through a local IPFS node or remote IPFS gateway. Then the content will be chunking and distributed to different peers. The content will have a unique identifier called contents ID, set in short, and you can alternatively give it an IPNS name. When the content consumer wants to fetch the content using the CID, IPFS will use the DHT, the distributed hash table, to find out where all the chunks of the CIDs are located. And then IPFS nodes will use the bit swap mechanism to fetch all the chunks of the contents. Here's the diagram of how IPFS is doing the contents ajaxing. As you can see in this diagram, it uses a Merkle-derived acyclic graphs, Merkle DAX in short, which are graph data structures where each node is content adjacent. This kind of similar as the Merkle tree structures you can find in the blockchain's data tree and stage tree. This diagram shows if you upload a folder to IPFS, how the IPFS will link all the contents inside the folder to the root folder CID. Each file and subfolder will also have their own unique CID, and they are using Merkle DAX to link together. It is the same structure for file CID and all its chunks. Each chunk will be hashed and also has its own CID, and will be linked with the root file CID in the Merkle DAX structure. And the file's microdex will be a subgraph of a larger microdex if this file belongs to a folder. And so with this mechanism, we can use content injection in IPFS stamp the location-based identifier in Web 2. You can see a traditional HTTP web page URL can be represented fully by content-based adjust, as you can see in this CID stream. As long as the content is unchanged, the CID will remain the same. This diagram shows an example of how to fetch data from IPFS. When user requires some content with its CID, the application will read the data from IPFS network. First, it will reach out to multiple IPFS gateway for content retrieval racing. The IPFS gateway has a local IPFS node running on it, which will use the DHT and bitswap mechanisms to fetch all the chunks from other IPFS peers. When the local IPFS node on the gateway retrieves all the chunks of the contents, it will return back the whole consolidated contents to the user. So the previous few slides are basic overview to the IPFS protocol. Actually, IPFS has more concepts and functionalities than what's shown here. Due to time limits, you can refer to the IPFS official document for more deeper information. Now let's have a look at the second layer, the MPOW minimal proof of work. MPOW is a zero trust storage proof layer. It is implemented based on the TEE, the Trusted Execution Environment technology. There are major three processes, the store process, the report process, and the verify process. As you can see in this diagram, first the data is transferred to the Crust server nodes through IPFS, and then it will use the TEE to seal and store the data locally. The second process is the report process, the dark lines here. The node will use the TEE to inspect and assign a work report periodically. The work report includes the incremental information of data storage work on this node, and then the work report will broadcast to the Crust mainnet chain. The third process is verify process, where the on-chain logic will verify whether the work report is valid and calculates the relative storage power for the nodes. Based on the TEE technology, the nodes in Crust Network can perform non-interactive zero-trust storage proof. This is a detailed look inside a Crust node. When the IPFS receives the file contents from the P2P network, it will invoke this program we call the S-worker, the storage worker, to do the content sealing using the TEE. S-worker will inspect, sign, and broadcast the work reports periodically to the Crust chain. TEE, the trust execution environment, is commonly known as an isolated processing environment in which applications can be securely executed irrespective of the rest of the system. There are multiple TEE solutions like IntelliSGX, ARM Trust Zone, and AMDSEV. Crust Network used the IntelliSGX as the TEE solution. Here's a brief diagram for IntelliSGX. The Intel CPU will create a special memory space called enclave, isolated from the operating system. The execution logic in the enclave is verifiable and tamper-proof, and data in the enclave cannot be read or processed by any program outside. The enclave is considered to be credible as long as it is verified. In order to make IPFS to work with S-worker to do data sealing and unsealing, Crust Network has customized the IPFS protocol implementations. As you can see in this diagram, the file blocks received by IPFS are sent to S-worker to seal and store. IPFS doesn't store the original file blocks anymore. Instead, it stores the file block index returned by the S-worker. IPFS can get the original file blocks by providing this block index to S-worker. Here's the content retrieval process. When a file block request coming, the IPFS sends the corresponding file block index to the S-worker to do the unsealing and gets the real file block data back. Then send this block data back to the requested node. Now let's have a look at the middle layer, the GPOS guarantee proof of stake. The GPOS is a POS-derived consensus protocol. like the NPOS, a user can stake to specific nodes to get staking rewards. The key difference is that each node has its own staking quota or set of staking limits decided by its proven storage resource and work. Therefore, GPOs encourage nodes to provide more storage resource to take more work and improve the security and robustness of the network. GPOs leverage the storage work reports generated by the MPOW storage proof to calculate the storage power. The more storage resource a node contributes, the higher stake limit it can attain. Which means if the node doesn't store enough real files, it will have a low stake limit. Any balance over the stake limit is not effective when calculating the staking rewards. Next is the DSM layer, which is the decentralized storage market. It allows the users to place storage orders on the chain, and the files specified in the storage order will be stored by the Crust server nodes. The DSM contains three major mechanisms. One is the pricing mechanisms. Storage order fee is calculated by the network according to file size, the storage period, and overall storage requirements and supply. Second is the benefits and rewards mechanism. The DSM market have multiple rewards and benefits mechanism to incentivize the storage nodes. Three, retrieval mechanism. The DSM includes another layer of incentives to encourage nodes to support data retrieval. Nodes providing better retrieval service will get higher ranking and have a better chance of getting more files quickly, thus getting more storage payments and staking income. The top layer is the products and SDK built on Crust Network. This is a list of products and SDK provided by Crust. We'll go through this in detail in the next two chapters. Okay, here's some quick introduction for the Crust products, which build on top of the Crust Network and SDK. First is the Crust apps, which is the enhanced management portal, which is developed based on the Polkadot JS apps. We can have a quick look at what we provided. This is Crust apps, which is based on the Polkadot JS apps. It provides general Polkadot JS functions like the account management, the network management, the democracy governance management, and the developer functions. You also provide Crust specific functions like the bridge. You can bridge the CIU token from Crust to Ethereum and Ethereum back to Crust. Also, the bridge to the Aaron and back and forth. Also, you can use the storage user function provided here for some very simple file upload. You can, let's say, upload a file with the like Crust apps. I will just show you. You can just sign and it will upload the files to the IPF scaleway, and then to get the maybe this is not reachable anyway. As this is the file I just uploaded before, and you can see that the Crust apps file, this is the CID returned from the IPFS scaleway. And here the data is already been stored on the Crust network. The 57 here is the 57 replicas, which means there are 57 physical server nodes across the world which have stored the files. You can also copy the file, the CID, the link address here to download. It just similar like this. It's just you can just paste it in the browser to get the files. This is the file content hello Crust apps. Okay, and the next is the Crust files. It's a personal web drive, like the traditional Dropbox or Google Drives. You can store your files in a decentralized and distributed storage network instead of cloud server. Okay, let me have a look. Can just go back to the here, like lockout first. We can connect with like MetaMask or Crust Wallet. If we connect with the MetaMask. Okay, we log in, and actually we can change to different Ethereum-based chains like the mainnet, the Optimus, and Arbitrum Blast based. Using the Crust files, you can like upload and share your files using the file sharing feature, and also you can use the vote feature to encrypt your file contents locally and then upload the encrypted file to the Crust network. This is the public functions that you can have many files you want. And also this is the text file. You can see there are 51 replicates already replicated in the whole Crust network. And for the vote feature, you can upload the file to the vote, which will generate a private key here locally in your browser, and the file content will be encrypted locally, and then the encrypted content will be uploaded to the Crust network, so that even any other ones knows the study will only get the encrypted contents. You can download the files using the functions here. We will do the encryption inside the Crust files. And next is the Crust Cloud, which is a cloud storage solution like the AWS S3 storage. It's also built on top of the IPFS and Crust network. You can create buckets of Crust Cloud, which is actually an NFT, but it's just similar like the AWS S3 bucket ID. And then you can store and retrieve the file using this bucket ID. Okay, and here's a quick look on the Crust Cloud. You have this the application. Due to time limit, I will just skip the demo for this Crust Cloud product. If you have interest, you can try it after the sharing. And the Crust IPFS Get is free and a handy open IPFS Explorer application. You can enter file CID and search. It will tell you how the IPFS stores the files. As you can see in this web page, this is the CID you want to search. It shows you how many webcasts have been replicated in the whole Crust network and its locations, and also how long will this file be guaranteed in this Crust storage. And also a list of the Crust server nodes who have stored this replicate. Now the next part, or the final part, is the how to develop and build with the Crust network. Before we dive into the source code part, let's have a look at the Crust IPFS W3 gateway and W3 pinning service. We have added a reverse proxy layer before the standard IPFS gateway. It provides the Web3 authentication ability. Let's say the client side. Let's say Alex wants to upload her file to IPFS. She only needs to do the following steps. Step 1 is to sign her public key with her private key using any Web3 wallet, and then she will get the signature. Step 2 is to call the standard IPFS API with the basic auth header. At the gateway side, after the Web3 authenticator receives the Alex request, first it will pass the header to extract the public key and the signature, and then it will pass the SIG with the public key to get the message back. It will determine whether the message and the public are the same. If the verification is passed, it will forward the request to the IPFS node in the backend. This is the Crust IPFS Web3 auth pinning service. After you have uploaded the file to gateway and have get the CID, you can call the pinning service to ping to the Crust network. First, you also use the same Web3 auth in the HTTP header as the Crust gateway service. The pinning service will then place the storage order on the Crust network to make files store and persist in the Crust storage nodes. The Crust pinning service will record and manage the on-chain status in its database, so you can query the file status through the pinning service API. Now, let's have a look at our first code example. We built this example using the gateway and the pinning service. Okay, you can also find the example at the official Crust GitHub report here, and also the wiki documents to describe this report. Here is the GitHub report I've downloaded here locally. This is the example start file with the pinning service. Let's have a quick look at the source code. Here's we define the gateway URL and the pinning service URL. Here we construct the auth header using the accounts for the signing and construct the auth header. And then the third step is using the standard IPFS library to add the files to the local IPF store order with my IPFS gateway, and then you get the CID back from the IPFS client. With the CID, we can just post a request to the pinning service, and using this kind of with the auth header and the CID retrieved. And then we can also query the ping status from the same pinning service server. It is a simple example with the pinning service. And next is here, just use the Crust SDK to place a storage order to the Crust mainnet directly. In this demo, the stuff file here is using the Crust SDK. For the first part, is similar to create auth header and add file using the IPF's standard client library. And the difference is that we can place the storage order with the SDK we provided. We just construct the transaction here, the place or storage order transaction of the file ID, file CID, the file size, the tips, and some other message to the this transaction. And then we are using the accounts to sign and send a transaction to the Crust mainnet chain. Okay, so just a few lines of code. You have already done the interaction of the Crust chain. Crust also develops event storage smart contracts, which can be deployed in any event compatible chains. Users can then place the storage order by interact with this smart contract with any familiar tools in Ethereum world. There will be the order merchants, which will listen to the events published by the contract and then place the storage order on the Crust mainnet chain. As you can see, these Crust demo reports to the event folder, like say the Arbitron demo. We define the contract just here and the API interface. With just a few lines of code, we sign the wallet and get the contract. First, we get the price provided by the storage contract, and then we place the order by interacting with this smart contract directly. Then you will get the files just stored on the Crust network. Next is the how to interact with the Crust parachain. We are running a Crust parachain on the Polkadot relay chain. Other parachains running in the Polkadot ecosystem can utilize the standard cross-chain communication mechanisms in Polkadot, which is named XCMP, to place a storage order request inside a substrate pallet directly. So other Polkadot parachains can just build and integrate the Crust decentralized storage capabilities fully on chain. And this is a simple XM code snippet on how to place a storage order to cross-chain. This code is written in Rust language and used inside substrate palette. Here we create a tuple for the page storage call. And the second step is to construct the cross-chain message for this call. And finally invoke the XMP message sender to send the message cross-chain. The multi-location here specifies the Crust parachain as the destination for the message. Next, you can also develop with Crust command line tools. So you can integrate it in any script automation. After you have installed the Crust CLI command line tool, you can use it in your terminal. First, log in with your account seeds, and then you can use the Crust CLI ping to ping any files you want. After ping success, you will get the CID back. And then we will use the Crust CLI publish command to publish the CID. This command will place a storage order successfully in the Crust mainnet chain. After that, you can check the ping status by using the status command. Next, you can also refer to the this GitHub reports to develop the how to integrate the published contents with the GitHub workflow actions. As you can see in this snippet, you can use the IPF upload action to upload your build artifacts to the IPFS gateway. And then the next is to use the IPFS Crust action to ping the CID back to the Crust network. After these two actions, then you can integrate your build process with the Crust network. Last part is the Subset Explorer. This Explorer provides comprehensive functions to query and analyze the on-chain data. I will not show a demo here. We can try later after the sharing. Okay, so that's all for today's sharings. These are the official contact channels for Crust. Welcome to follow. Okay, that's all for today as meeting. So let me hand it back to the host.
Okay. Thank you, Brian. Guys, if you have any questions, you can ask. I can forward to Brian. For now, I haven't seen any questions yet, so I'm just going to share my screen.
Okay.
Okay, cool. Yeah, just remind you if you want to try to have a chance to win the travel grants, you need to drop your name plus your project name or name plus individual。好如果大家有什么疑问现在还可以这个发出来，然后可以同步给老师。然后如果您想获取这个travel grants 这个奖励您就需要现在把这个姓名和项目名，包括如果您没有团队呢，那就是姓名加个人然后发到这个评论区。OK， 行，然后现在应该是没有什么疑问了。然后下周呢，其实周六周日，包括下下周的周六周日，我们应该也是会安排这个 workshop 的然后大家其实关注这个 DAO Hacks 就可以实时我们都会有这个更新然后包括在群里大家一定要关注一下对，行，然后没有报名的同学没有报名的同学您可以扫描这个黑客松的二维码进行报名。然后我也希望呢，就是同学们在这些分享中获得这个深入的收获和成长。然后感谢大家参与，也祝愿呢每位参赛者能在项目中取得这个出色的成果。OK， so if you have not registered yet, you can scan and register. Use the QR code from the the right side. And finally, I hope that all the participants here can gain in-depth and grow from the sharings. Thank you for participating today. I wish every participant to achieve outstanding results in the project. I'll see you next weekend. 好大家下周末见，谢谢大家，拜拜。
好，谢谢主持人。
谢谢，再见。
谢谢，拜拜。
好，拜拜。